All right, so what if I told you that a really bitter, century-old feud between two Russian mathematicians is actually the secret behind solving some of today's biggest questions? I mean, it's this crazy story that ties together poetry, politics, and, believe it or not, some of the most powerful technologies we've ever come up with.
Okay, think about this for a second. How on earth are shuffling a deck of cards, nuclear bombs, and Google search all connected? It sounds totally impossible, right? A weapon of mass destruction and the thing you use to look up cat videos. But it turns out they are. They, and even a simple game of chance, are all run by the exact same strange predictive math.
So, let's set the scene. We're going back to 1905 Russia. The whole empire is in chaos, right? You've got socialist groups rising up against the Tsar, and this political fight, it was so intense it got into everything, every corner of society. And somehow it even spilled over into the world of pure mathematics.
And right at the heart of this mathematical smackdown were two guys who were polar opposites. First, you've got Pavel Nekrasov. He was a big-shot czarist, super religious, and he was convinced, absolutely convinced, that math could prove free will exists. Then you have his rival, Andrei Markov. Markov was a hardcore atheist, a socialist, and he thought what Nekrasov was doing was just an abuse of everything math stood for. So he made it his personal mission to tear Nekrasov's argument to shreds.
So their whole fight was about this one central idea in probability, the law of large numbers. You know this one, even if you don't know the name. Think about flipping a coin. Flip it 10 times, you might get, say, 6 heads. But flip it 1,000 times, you're going to get really close to a perfect 50-50 split. Now, for like 200 years, mathematicians all agreed this law only worked for independent events, where one coin flip has zero effect on the next one. And that one little word, independent, that's where the whole fight began.
Okay, so Nekrasov, he takes this idea and makes a pretty wild leap. He's looking at social stats, stuff like marriage rates each year, and he notices they're weirdly stable. So he thinks, hey, if these big social numbers follow the law of large numbers, then the little individual decisions that make them up, like choosing to get married, must be independent acts of free will. For him, this was huge. Free will wasn't just some philosophical idea anymore. He thought he could actually measure it with science.
Well, Markov heard this and he was livid, absolutely furious. He thought connecting a mathematical rule to something as complex as human free will was just ridiculous. So he goes on this mission, right? He's going to prove Nekrasov wrong by showing that you can get those same stable, predictable results even when events depend on each other. He wanted to prove that this whole independence thing wasn't the be-all and end-all.
But to prove his point, Markov needed the right kind of system. He needed something where it was super obvious that one event influenced the next. And where did he find the perfect data to do it? Well, in a pretty unexpected place, right in the middle of a classic piece of Russian literature.
So here's what he did. He took 20,000 letters from Pushkin's famous poem Eugene Onegin, and he did the math. He figured if every letter was totally independent, the odds of two vowels showing up back-to-back should be about 18%. But then he actually sat there and counted, and the real number? Just 6%. Boom! That was his proof. The letters in a text are not independent. I mean, think about it. The letter Q is almost always followed by a U, right? The next letter definitely depends on the one that came before it. So with this data, Markov basically built a little prediction machine. He figured out the exact probability that a consonant would follow a vowel, or a vowel would follow a vowel, and so on. He created this simple system, a chain of events that just followed those rules. He'd start with a letter, and then based on the odds, it would spit out the next one and the next one. And here's the crazy part. Even though each new letter only depended on the single letter right before it, when he let this thing run for thousands of letters, the final text had the exact same ratio of vowels to consonants as the original poem.
And just like that, he completely destroyed Nekrasov's whole argument. He even ended his paper with this epic final takedown. Thus, free will is not necessary to do probability. Mic drop. The point was, Markov proved you don't need independence for this stuff to work. In the process, he'd accidentally invented this powerful new tool, the Markov chain. But honestly, nobody really cared at the time. For him, it was just about winning the argument.
But what Markov couldn't possibly have known was that this little tool he invented to win a fight would, decades later, become absolutely critical to one of the most secret and high-stakes projects in all of human history.
Okay, let's jump forward in time to the Manhattan Project. The scientists there are trying to build the first atomic bomb, and they've hit a massive wall. To figure out if the bomb will even work, they have to predict what trillions upon trillions of neutrons are going to do as they split atoms in a chain reaction. The sheer number of possible interactions was just astronomical. There was no way to calculate it directly.
The breakthrough came from a totally unexpected source. There was this mathematician, Stanislaw Lamb, and he was recovering from a brain inflammation that almost killed him. And as he's lying there, just to pass the time, he's playing solitaire. And he starts wondering, what are the actual odds of winning a game of solitaire? He realized there's no way to calculate it perfectly. But, and this is the key insight, he figured he could get a really good estimate just by playing hundreds of games and writing down how many times he won.
So Ulam shares this idea with the legendary John von Neumann, and you can just imagine the light bulb going off over von Neumann's head. He immediately gets the power of statistical sampling, but he also spots a crucial difference. See, every game of solitaire is independent of the last one, but a neutron? No way. Its path is totally dependent on what it just bounced off of. It was a chain of dependent events, and von Neumann realized exactly what they needed: a Markov chain.
So they took this idea and ran with it, building these incredible new computer simulations. They gave it a fun little code name, the Monte Carlo method, named after the casino, of course. What they did was model the path of a single neutron as a Markov chain, and then they'd simulate that path thousands and thousands of times. And all that work let them calculate one single all-important number, which they called k, the multiplication factor. And k told them everything. If k was less than 1, the reaction just dies out. If k is greater than 1, you get a massive exponential chain reaction. They had finally figured out how to know if they actually had a bomb on their hands.
All right, fast forward again. It's the 1990s now, and that very same idea gets dusted off to solve a totally different kind of explosion. Not a nuclear one, but an information explosion. The internet was blowing up so fast, it was becoming this giant, messy library. How could anyone possibly find what they were looking for?
See, the early search engines like Yahoo had a huge flaw. They basically just counted how many times a keyword showed up on a page, and that was super easy to game. People would just spam a page with invisible keywords, white text on a white background. So these search engines could tell you if a page was relevant, but they had absolutely no way of telling you if it was any good.
And then along came two Stanford PhD students. You might have heard of them, Larry Page and Sergey Brin. They had a genius idea. They thought, what if we treat every link from one page to another as a vote of confidence, like an endorsement? To measure a page's quality, they dreamed up this imaginary random surfer who just clicks on links at random, hopping from page to page. A really high-quality page would be one that the surfer just happens to land on all the time. And just like that, the entire web became one gigantic Markov chain. A page's rank was nothing more than the probability that a random surfer would be on that page at any given time.
Now, they did run into one little problem. What if the random surfer gets trapped in a little corner of the web, just clicking between pages that only link to each other? They'd be stuck in a loop forever. So they came up with a really clever solution. They gave the surfer a simple rule. 85% of the time, click a link on the page, but the other 15% of the time, the surfer gets bored and just teleports to a completely random page anywhere on the internet. And that little trick, that damping factor, made all the difference. It guaranteed the surfer would eventually visit every nook and cranny of the web, which gave a much more accurate score for every single page.
So think about this journey we've just been on. From a political spat in Russia to the Manhattan Project to building Google. What is the secret sauce that makes Markov chains so powerful and so useful in all these different fields? Well, it all boils down to one simple yet incredibly powerful idea. And once you get it, we can finally answer that question I asked you at the very beginning.
Here it is. The big secret is something called the memoryless property, and it's a game changer. For a ton of really complex systems, think about the weather or stock prices or even the words in the sentence, you'd assume you need to know their entire long, complicated history to predict what's going to happen next. But what Markov discovered is that for a lot of these systems, you don't. You can make surprisingly accurate predictions by looking only at where you are right now, the current state, and completely ignoring how you got there.
And that brings us all the way back to shuffling cards. So if you think about it, every possible order of a deck of cards is a state in a massive Markov chain. And every time you shuffle, that's a transition to a new state. The question is, how many shuffles does it take to get to a point where any order is just as likely as any other? In other words, when is the deck truly random?
Well, the answer, which we get thanks to Markov chains, is genuinely shocking. If you're doing a perfect riffle shuffle, where you split the deck in half and perfectly weave them together, it takes just 7 shuffles. That's it, 7. But what about that clumsy overhand shuffle, where you're just moving chunks from the back to the front? You'd better settle in, because for that, it takes over 2,000 shuffles. It's an unbelievably different answer, and it comes from the exact same piece of math.
And really, that's the big takeaway here. This whole powerful idea started because one guy wanted to win an argument. It was born from a petty academic feud, and yet it gave us this incredible tool to see the world differently. It let us understand probability and dependence in a way no one had before. It helped build nuclear bombs, it organized the entire internet, and today it's the engine behind the AI that's predicting the very next word you type on your phone. It just goes to show you, sometimes the most complex problems in the world are just a matter of cooking up the right Markov chain.